Electrostatics 4. In this lecture, we derive the expressions for field and potential due to an electric dipole. We study the behavior of a smear of charge. We also establish the expressions for torque and energy of a dipole in an external field, which is the basis for food cooking in a microwave. Beautiful picture taken from the internet based on a program in Python of a linear quadrupole. Not only do the black lines indicate the direction of the electric field lines, but the gradation in color is also indicative of the electric field strength. Electric quadrupole is formed by two equal and opposite dipoles that do not coincide in space so that the electric effects do not cancel out at distant points. We assume that D is very much less than R. The potential at a point P due to the quadrupole on the right is given by. Now, the potential at a point R is given by 1 upon 4 pi epsilon naught Q upon R1 plus Q upon R2 minus 2Q upon R. R1 square is equal to R square plus D square minus 2 dr cos theta. 1 upon R1 will therefore be equal to 1 upon R square plus D square minus 2 dr cos theta raised to the power half. Therefore, this is equal to 1 upon R 1 plus D square upon R square minus 2D upon R cos theta raised to the power minus half. Expanding binomially, we will have 1 upon R 1 minus half D square by R square minus 2D upon R cos theta plus half into 3 by 2 upon 2 factorial D square by R square minus 2D upon R cos theta. Plus there will be higher order terms which have been neglected. Now let us open the square term to get D square upon R square minus 2D upon R cos theta whole square equal to D to the power 4 upon R to the power of 4 minus 2 into 2 D cube by R cube cos theta plus 4 D square upon R square cos square theta. We will neglect D to the power of 4 upon R to the power of 4 minus 2 into 2 D cubed by R cubed cos theta. We will be left with 1 upon R open brackets 1 minus half D square by R square minus 2D upon R cos theta plus half 3 half upon 2 factorial for D square by R square cos square theta. Continuing, we will get 1 upon R 1 minus half D square by R square minus 2D upon R cos theta plus 3 half D square by R square cos square theta, which is equal to 1 half 1 plus D upon R cos theta plus half D square by R square 3 cos square theta minus 1. Similarly, 1 upon R by 2 is equal to 1 upon R square plus D square minus 2 dr cos pi minus theta raised to the power half, which is 1 upon R2 1 upon R square plus D square plus 2 dr cos theta raised to the power of half. As before, if we turn this into a binomial expansion, we will get 1 upon R 1 minus D by R plus half D square by R square 3 cos square theta minus 1 raised to the power minus half. The expression for phi r is therefore equal to 1 upon 4 pi q by r1 plus q by r2 minus 2 q by r, which is given by q by 4 pi epsilon naught r 1 plus d by r cos theta plus half d square by r square 3 cos square theta minus 1 plus 1 minus d by r cos theta plus half d square by r square 3 cos square theta minus 1 minus 2, which simplifies to q by 4 pi epsilon naught d square by r square 3 cos square theta minus 1. Therefore, the potential due to a linear quadrupole varies inversely as the cube of the distance. E is equal to minus grad phi. So, Ex is equal to minus del phi by del x, which is equal to minus del by del x of q by 4 pi epsilon naught r d square by r square 3 cos square theta minus 1. From the figure, we can see that cos theta is equal to x upon r. Therefore, 3 cos square theta minus 1 upon r cubed is going to be equal to 3x square by r to the power of 5 minus 1 upon r cubed. Now, delta r by delta x is equal to half x square plus y square plus z square raised to the power minus half into 2x. Therefore, delta r by delta x is simply equal to x upon r. Now, if we differentiate 3x square by r to the power of 5 minus 1 upon r cubed with respect to x, we will get 6x upon r to the power of 5 minus 15x square upon r to the power of 6 delta r by delta x plus 3 upon r to the power of 4 delta r by delta x, which is equal to 6x upon r to the power of 5 minus 15x square upon r to the power of 6 x upon r plus 3 upon r to the power of 4 x upon r, which is equal to 6 cos theta upon r to the power of 4 minus 15 cos cube theta upon r to the power of 4 plus 3 cos theta upon r to the power of 4, which yields 9 cos theta upon r to the power of 4 minus 15 cos cube theta upon r to the power of 4. Now Ex is equal to minus del phi by del x, which is equal to 3q upon 4 pi epsilon naught d square upon r to the power of 4 5 cos cube theta minus 3 cos theta. Similarly, Ey will be equal to minus del phi by del y, which is minus del by del y of q upon 4 pi epsilon naught r d squared upon r squared 3 cos square theta minus 1. Now del by del y of 3x square upon r to the power of 5 minus 1 upon r to the power of 3 yields minus 15x square upon r to the power of 6 delta r by delta y plus 3 by r to the power of 4 delta r by delta y, which is minus 15x square upon r to the power of 6 y by r plus 3 upon r to the power of 4 y by r. So Ey is equal to 3q d square upon 4 pi epsilon naught 5 cos square theta minus 1 y upon r to the power of 5. Similarly, Ez will also come out to be equal to 3q d square upon 4 pi epsilon naught 5 cos square theta minus 1 z upon r to the power of 5. So Ex will be equal to 3q upon 4 pi epsilon naught d square upon r to the power of 4 5 cos cube theta minus 3 cos theta. Therefore, the resultant electric field is given by under root of Ex square plus Ey square plus Ez square, which is 3qd square upon 4 pi epsilon naught 1 upon r to the power of 4 into under root of 5 cos cube theta minus 3 cos theta whole square plus 5 cos square theta minus 1 raised to the power 2 y square plus z square upon r square. Now, y square plus z square upon r square is simply sine square theta, which is 1 minus cos square theta. Hence, expression under the root sign now becomes 3qd square upon 4 pi epsilon naught 1 upon r to the power of 4 5 cos to the power 4 theta minus 2 cos square theta plus 1 raised to the power half. The axis of the quadrupole lies along the x-axis. Therefore, for a point lying along the axis of the quadrupole at theta equal to 0, we have E parallel equal to 3qd square upon 4 pi epsilon naught 1 upon r to the power of 4 5 minus 2 plus 1 raised to the power half, which is equal to 6 qd square upon 4 pi epsilon naught 1 upon r to the power of 4. For a point lying on a line perpendicular to the axis and passing through its center, theta is equal to 90 degrees. So E perpendicular is equal to 3q d square upon 4 pi epsilon naught 1 upon r to the power of 4. Hence, the electric field on the axis of a linear quadrupole is twice that on the axis perpendicular to its own axis and passing through it. We now come to the dipole approximation to an arbitrary charge distribution. Assume a random distribution of charge. We are interested in fields far away from this arbitrary charge distribution. Consider a charge Qi located at a displacement di from the origin. We wish to determine the potential at a point P located at a distance r from the origin and a distance ri from the charge Qi. Assume that r is very much larger than di max. The potential at a point P due to a collection of discrete charges is the algebraic sum of the potentials due to each charge. Thus, phi P is equal to 1 upon 4 pi epsilon naught summation over I Qi upon Ri. To a first approximation, di plus Ri is equal to r. So, Ri is equal to r minus di. Now, r is very much larger than di max. Therefore, Ri is approximately equal to r. Phi P is equal to 1 upon 4 pi epsilon naught r summation over I Qi. But if the number of positive and negative charges is equal, the resultant potential is effectively 0. Yet, it has been experimentally observed that such a smear of charge does give a measurable electric effect even at far off distances. Hence, we need to improve our approximation, and the way to do it is as follows. Reconsider the distance triangle OQIP. Drop a perpendicular from Qi onto OP. Let it intersect at Q. Now, OQ is simply equal to di dot r. It represents the projection of OQI onto OP. Now, since r is very much larger than di, we can write r minus di equal to r minus di dot r. What we are doing is simply improving upon the first approximation. So when we have Ri equal to R minus di dot R, taking the reciprocal of Ri, we will have 1 upon R minus di dot R. Taking 1 upon R outside the brackets, within the brackets we will be left with 1 minus di dot R upon R. Let's carry out a binomial expansion. We will have 1 upon Ri approximately equal to 1 upon R 1 plus di dot R upon R if we retain only the first order. So phi p is equal to 1 upon 4 pi epsilon naught summation over I qi upon Ri. So phi p is equal to 1 upon 4 pi epsilon naught summation over I qi upon R 1 plus di dot R upon R. So phi p is equal to 1 upon 4 pi epsilon naught summation over I qi plus 1 upon 4 pi epsilon naught summation over I qi over R di dot R upon R. Now, since the number of positive and negative charges are equal, the first term is 0, but qi di is equal to pi, the dipole moment. Phi p is equal to 1 upon 4 pi epsilon naught pi dot R upon R square. And this is the dipole contribution. Let us next consider a dipole in an electric field, which will give us the force and torque on a dipole. When we place an electric dipole in an external electric field, the force on the positive charge will be in one direction, the force on the negative charge will be in an opposite direction. The forces on plus q and minus q will have equal magnitudes but opposite directions. The net force on the dipole due to the external field is effectively zero, but there is a net torque about its center of mass that tends to rotate to bring the dipole into an alignment with the applied field. The torque on each charge is tau equal to Fr perpendicular. The net torque about the center of the dipole due to the two forces has a magnitude Ft sin theta. Its direction is perpendicular to the plane of the page and is into the page. The right hand side diagram shows the vector relationship between the dipole moment P and the electric field E. The resultant torque tau on the dipole points into the page. Tau is equal to QED sin theta, which is QDE sin theta, which is equal to PE sin theta. In a vector form, tau is equal to P cross E. Since electrostatic force is conservative, we can just as well use the work done by the electric field in turning the dipole through an angle theta. The work done by the external field in turning the dipole from an initial angle theta 0 to a final angle theta is W equal to integral dW, which is equal to integral theta 0 to theta tau dot d theta, which is equal to theta 0 to theta minus tau d theta. The minus sign means that the torque decreases the angle theta. Also, tau and d theta are in opposite directions. Therefore, W is equal to minus integral theta 0 to theta Pe sin theta d theta, which is equal to minus Pe integral theta 0 to theta sin theta d theta, which is equal to Pe cos theta minus cos theta 0. Since work done by the agent that produces the external field is equal to the negative of the change in the potential energy of the system plus the dipole, we have delta U equal to U theta minus U theta 0, which is minus W, which is equal to minus Pe cos theta minus cos theta 0. We can arbitrarily define the reference angle theta 0 to be 90 degrees and choose the potential energy U theta 0 to be 0 at that angle. At any angle, therefore, the potential energy then is given by U is equal to minus Pe cos theta, or U is equal to minus P dot E in a vector form. The potential energy is a minimum when the electric field and dipole moment vectors are parallel. We are now in a position to understand how food cooks in a microwave and dipoles. A water molecule has an electric dipole moment. In a microwave oven, the electric field of the microwave radiation tends to rotate the dipole moment of the water molecules into an alignment with the field. A free water molecule would simply oscillate back and forth about its equilibrium position. But in materials such as food, interactions between neighboring water molecules convert the angular motion due to the torque. Or equivalently, the kinetic energy of the rotation arising from the decreased potential energy of the dipole in the field into internal energy. The directions of the field reverse every 2 into 10 power minus 10 seconds, and as dipole moments continually try to follow the field, they transfer energy that cooks the food. The motion of dipole in an external field then can be interpreted as number 1, the torque that rotates the dipole into alignment with the field, or 2, the potential energy that becomes a minimum when the dipole is aligned with the field. The choice of interpretation is based on the convenience in application to a particular problem.